This. Now, here's the rewritten TTS-ready transcript.
Welcome to the deep dive. We're jumping into some source material today to really get a handle on algebraic factorization for you.
That's right, factorization. It sounds maybe a bit technical, but the core idea is pretty simple. It's like finding the basic ingredients of an expression.
The building blocks, yeah. Breaking it down.
Exactly. Finding simpler bits that multiply together to give you the original thing. You know, the source actually defines it as writing an expression as the product of factors.
Okay, so it's like working backwards from multiplication. Like instead of expanding brackets, we're creating them.
Precisely. Doing the opposite of expanding. We start with the result and find the multiplication that made it.
Gotcha. And the source lays out a few key methods for doing this, right?
It does. The first one, and maybe the most fundamental, is taking out the common factor.
Right. Looking for something that's in every part of the expression. That feels like the first place you'd look.
It usually is. It's basically the distributive property, just, in reverse.
Yeah.
You find the biggest thing, the greatest common monomial factor that divides into all the terms.
Okay, so find the shared piece, pull it out front, and then what's left inside the brackets is just the original terms divided by that common factor.
That's exactly the process. Like the source gives the example $4y, 8y22. You look at both terms.
Okay, I see a 4 in both and a y in both. So 4y.
4y, exactly. That's your greatest common factor. So you pull out 4y.
And you're left with, let's see, 4y ISY divided by 4y is just 6, so. And 8y22 divided by 4y is 2y time. So 4y by 2y.
Perfect. You factored it. You've pulled out the common part.
Okay, check for common factors first, always.
Yeah.
But what if there isn't one single thing common to all the terms?
Good question. That leads straight into what the source calls type 2 grouping. This is handy when, maybe you have 4 terms or 6.
And no single factor works for everything.
Right. But you might find common factors if you sort of pair terms up.
Like looking for smaller patterns within the bigger expression. The example x plus bx plus a plus bidon seems like that. Nothing's in all 4.
Exactly. So with grouping, the idea is you group terms strategically. Maybe the first 2 and the last 2.
Okay, so dx plus bx is one group, and d plus bi is another.
Yep. And now you factor each little group using the common factor method we just talked about.
Right, so xs plus bxe, that's 6xa plus b, and a plus bi is dA plus b.
See that? Now look at what you've got. 6a plus b plus ya plus b do.
Okay, I see it. Now the a plus b dollar tart itself is common to both chunks.
Exactly. That's the trick with grouping. You've revealed a common binomial factor, so now you can factor that out.
So you pull out the a plus b, and what's left is x to x plus y, giving you a plus b, x plus y. Wow, okay. That's clever.
It is. It's like a 2-step common factor process almost.
So common factors grouping. What's the third main type the source mentions?
The third one is about spotting a very specific structure. It's called type 3, difference of 2 squares.
Difference of 2 squares. Okay, the name kind of gives it away. You subtraction and 2 things that are perfect squares.
Precisely. It relies on knowing the identity. A plus B, AB equals $T$, B22.
Yeah.
If you see something in the form $8, B22,
You can immediately jump to the factored form.
you bet. You just write it as square root of the first plus square root of the second times square root of the first square root of the second.
Like the example, 9 by $2, 64y at 2. And 9 by 2 is 3 by 2 LSRs, and 64y22 is 8y22.
Yep, perfect squares. And there's a minus sign between them. It fits the pattern.
So $82 and 8y, it factors to 3x plus 8y, 3 by 8y.
That's it. Recognizing that pattern saves a lot of work. The source even shows how it helps with numbers, like $67, $33. It's 67 plus 33. $67, $33. Much easier.
Right. And sometimes, I guess you have to use more than one method. The source calls that complete factorization.
Yes, exactly. Often the first step is always to look for a common factor. Always. Pull that out first.
And then what's left inside the bracket might need grouping, or it might be a difference of squares.
Could be either, or something else maybe. The goal is to keep factoring until you can't break it down any further, like 2 by 2, $81.
Okay, first step, common factor. Looks like 2.
Right. Pull out the 2. You get 2 by 2, $4.
And now inside the brackets, 6 by dollars, $4. Hey, that's 6 by $2, 2 quarters. Hey, that's 6 by 2 months, $202, a difference of 2 squares.
You got it. So that part factors again.
Into 6BA plus 2,
Yeah.
not $2. So the whole thing, fully factor, is $2x plus 2 at $2.
That's complete factorization. Applying the tools until each factor is as simple as possible.
So pulling it all together for you listening, we've seen from the source material that factorization is really about reverse engineering multiplication. finding those basic products.
Whether that's by pulling out common stuff, grouping cleverly, or spotting those special patterns like the difference of squares.
It's all about breaking down complexity into simpler multiplicative parts, deconstructing it.
Finding the structure underneath.
Exactly. And maybe here's a final thought to leave you with. Think about how powerful that skill is. Recognizing patterns, breaking complex things down, pulling out what's common, grouping related bits, spotting known structures.
Yeah, it's a way of thinking.
It really is.
Yeah.
It's not just for algebra class, right? Consider how you might approach complex problems or situations in, well, any field. Can you find common threads? Can you group related challenges? Is there an underlying pattern that suggests a known solution path? Really look for those hidden structures. It's a useful lens for almost anything.